Welcome back to day 2 of our equilibrium notes. Today we're going to talk about how to calculate equilibrium constant expressions or do calculations that involve equilibrium constant expressions. One of the things that the KEQ or the equilibrium constant expression tells you about a reaction is whether you have more products or you have more reactants at equilibrium. A way you can do this is by looking at the value of your KEQ. If your KEQ is greater than 1, then you have more products than reactants at equilibrium. Because your products are on top, you're dividing by a smaller number of the reactants, you're going to get an answer that's greater than 1. So we would say that products are favored then. If our KEQ is less than 1, then more reactants than products occur at equilibrium. You're dividing by a larger number, so your answer is going to come out being less than 1. Therefore, our reactants, we would say, are favored. So last time we looked at notes, one of the things that we talked about was how to write equilibrium constant expressions. Whenever you're doing this type of calculation, that's always where you're going to want to start, is by writing out your KEQ or your equilibrium constant expression. So for problem A here, it says find the KEQ for the following reaction, and then it gives you the following concentrations. I'm not going to read them off to you because you guys can see them there in front of you. So like I said, the first thing we want to start with is by writing our equilibrium constant expressions. It's products over reactants. And so here we have methane gas, CH4. It's got a coefficient of 1, so that'd be to the power of 1. And we don't have to write the power of 1, so I'm not going to really write those anymore. Multiplied by the concentration of water divided by the concentration of carbon monoxide and the concentration of hydrogen gas. And that value would be cubed because we have a coefficient of 3 there. All of these substances here are gases. Therefore, we include all of them in our KEQ calculation and our KEQ expression. They gave me the concentrations of all 4 of these, so I'm going to plug them into the equation now that I just wrote there. So the concentration of methane was 0.933 molar. The concentration of water is also 0.933 molar. The concentration of carbon monoxide there is 0.525 molar. And the concentration of hydrogen gas is 1.58. And that is going to be cubed there. So if I were typing in this calculation in my calculator, I would cube 1.58 first, and then multiply it by 0.525. And then I would take 0.933, square it, and divide it by whatever that previous answer was. And when I do that, my equilibrium constant value comes out to be 0.420. I have wonderful news for you. There is no units that you need to write for your equilibrium constant values. So there's no units for KEQ, unlike last chapter that we did. So now that we found what the KEQ for that reaction is at that given temperature, we need to identify what is favored here, reactants or products. Well, since my KEQ here is less than 1, that means reactants are favored in this reaction. That means the concentration of my reactants are greater than that of the concentration of my products. All right, let's look at the next problem here. The following system was held at constant temperature and allowed to reach equilibrium, and the concentrations were measured. Again, I'm not going to list those off to you. It says calculate the equilibrium constant. So I need to calculate what my KEQ is. In looking at the reaction, we have gas, 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 solid. Because that's a solid, I am not going to include that in my KEQ calculation or in my KEQ expression. So we're going to start by writing that expression. So it's products over reactants, concentration of carbon monoxide times the concentration of hydrogen. Both have a coefficient of 1. divided by the concentration of water. Again, I don't include carbon because that was a solid. All of them have a coefficient of 1. So they're all to the power of 1, which again is understood. So then I'm going to plug in what I know. I know the concentration of carbon dioxide is 1.0 times 10 to the negative third. I know the concentration of hydrogen is 3.1 times 10 to the negative third. And I know the concentration of water is 3.1 times 10 to the negative first. I would go and calculate that out. 1.0 times 10 negative third times 3.1 times 10 negative third equals, and then divide it by the 3.1 times 10 negative first. And I get a KEQ value here of pretty small, 9.7 times 10 to the negative sixth. This KEQ value is definitely less than 1, which means that reactants would be favored here. In the next problem, it tells us to calculate the equilibrium concentration of ammonia. The equilibrium concentration of nitrogen and the concentration of hydrogen, so they tell us what those values are. And then they also give us the KEQ for this reaction. So unlike the previous problems, we now know what that KEQ is. And since that number is less than 1, I can go ahead and answer this question right away. Reactants are what's favored because that value is less than 1. My goal this time is to really find what the equilibrium concentration of ammonia is. So I still start off by writing my equilibrium constant expression. It's going to be nitrogen times hydrogen. I have no idea why that parenthesis is there. Google Docs do all kinds of goofy things to notes and papers, so I'm sure you guys have noticed that before. And then I'm going to divide that by ammonia. And since my coefficient there is 2, I'm going to square it. I know what my KEQ value was. It was 1.7 times 10 to the negative second. I know that nitrogen's concentration is 0.55. And I know that hydrogen's concentration is 1.65. And that value is cubed. What I don't know is ammonia. And when I don't know something and I'm solving for it, I'm going to use X. So we're going to say ammonia is X, and that value is squared. So then I'm going to go through and solve for this problem. Let's see here. So 0.55 times 1.65 cubed, that value there comes out to be 2.5, and I'm still over X squared. So simplifying that, I have 1.7 times 10 to the negative second equals 2.5 over X squared. Now I want to get X squared by itself and get rid of the 1.7 times 10 negative 2. So since X squared is on the bottom, I got to solve for it on top. It's the only way I can solve for it. Multiply both sides by X squared, and then you divide by the 1.7 times 10 to the negative 2. I know this looks messy. I apologize. So what we end up with then is X squared equals whatever 2.5 times 10 negative 7, 10 to the negative second equals. And that comes out to be 150. So the square root of 150 to get just X is 12. Now, my question was not, what is the value of X? My question is, what is the value for the equilibrium concentration of ammonia? X was representative of ammonia, of NH3. So to finalize my answer here, I'm going to say that the concentration of ammonia is 12 molar. Concentration is measured in molarity. So this does have a unit when I find that, and that is molar then. All right, the last one we're going to look at today. Calculate the equilibrium concentrations of oxygen and nitrogen. Assume they are equal. The equilibrium concentration of nitrogen monoxide is 0.55 molar. And the KEQ for this reaction at room temperature is 1.75 times 10 to the third power. Again, I'm giving you the KEQ right away. We can see that number is definitely greater than 1. Therefore, our products are favored. So we can answer that question right away. Now, in order to find the concentration of oxygen in nitrogen gas, I'm going to start by writing my equilibrium constant expression. KEQ equals nitrogen monoxide to the second power, because I have a coefficient of 2 there, divided by the concentration of oxygen and the concentration of nitrogen. Everything is gases there, so they're all included in my equilibrium constant expression. Let's see here. So my KEQ is 1.75 times 10 to the third. Nitrogen monoxide's concentration I know is 0.55 molar, and that is squared. And that's going to be divided by oxygen's concentration and nitrogen's concentration. And since I don't know those, that's what I was trying to find there, I'm going to plug in X for both of those. So simplifying this, I get 1.75 times 10 to the third equals 0.30. 0.55 squared is 0.30 with sig figs over X squared. Now again, I cannot solve for X squared on the bottom. I have to get it on top. So I'm going to multiply both sides by X squared. And then I'm going to divide both sides by 1.75 times 10 to the third. So when I do that, I get X squared equals 1.7 times 10 to the negative fourth. And to find X there, I'm going to take the square root of that number. And when I take that square root, I get 0.013. Again, our goal was not to solve for X in this problem, but to find the concentrations of oxygen and nitrogen gas. So I'm going to formalize this and say nitrogen and oxygen equal 0.013 molar. Because I'm finding concentrations, we label that as molar there. That is it for day 2 notes of equilibrium. Next time we take notes, we're going to be looking at Le Chatelier's principle.